So, yeah, fingers crossed. And then we'll take it from there. I'm broadly working under the assumption that some alternatives will be presented in some shape or form. But yeah, I'll keep you guys in the loop as I know what the plans are, and it's probably, I suspect at this stage it's going to be some sort of hybrid model. So we'll go from there. All right, so today we'll sort of going a bit deeper into hydrothermal fluids and alteration. Tomorrow we'll look a bit more at alteration, so this will help with the first assignment. And I will bring some samples in and we can talk through some examples tomorrow about different kinds of hydrothermal alteration and what they might tell us. So bits and pieces of this broadly being covered already, so apologies for that. But, we'll go into the important parts a bit in a bit more detail. So we've gone through the main reservoirs, and we'll start to get more into the behaviour of hydrothermal fluids and their chemical composition and why that matters for metals and also for alteration, which we use as a vector to look for metals. So we've seen this diagram before. The main types of hydrothermal fluid, where they come from, and obviously where they originate from has a big controlling factor on their composition and nature, especially things like salinity, pH, and oxidation. And they're things that will influence how well they can carry metals, also when they might deposit metals. For example, if you have, say, the interaction of magmatic fluid with meteoric fluid, you have a change in that dynamic or mixing of those two fluids, and the composition changes, and they can actually lead to the deposition of the metals. So that can be a key indicator of where different ores might form in relation to that ability to carry them. So generally, most of them are H2O. You also get CO2 rich ones. So calcite veins and things like that are commonly going to be rich in CO2, sort of makes broad sense because they're forming calcium carbonate, whereas quartz ones are mainly the water dominated ones. And you get a mix, but we also have these chemical species with various combinations: chloride, boron, fluorine, hydrogen sulfide. And they are actually many of the important ones for carrying metals. We'll get into that a bit later. And their composition obviously varies depending on source and nature of the fluid. So, firstly, how do fluids and hydrothermal fluids move through the crust? So, they follow broad gradients that can be thermally or pressure controlled. The most one deep in the crust is related to actually fluid pressure. So the same as groundwater moves from places of high hydraulic head to low hydraulic head, hydrothermal fluid will move from places of high pressure to low pressure. So in a broad sense, just like most other physical processes, involving pressure systems, but in the crust, to change those pressure gradients is largely driven by deformation. So deformation will create space for fluid to move into, so it's got lower fluid pressure, or it will cause fluid pressure to rise. And of course, that's inherently linked with the source of the fluid. So hydrothermal fluid can also broadly control where it goes by fracturing other rocks if it pressurizes and moving further up towards the surface. So it's a highly dynamic process that varies depending on how deep we are, what rocks are they're what processes we're looking at. So thermally controlled ones would be like mid-ocean ridges, like we discussed last week, where it circulates, heats up, and convects. But things like orogenic process, aerogenic gold, things like that are more controlled by fluid moving depending on deformation. One of the main conduits in the crust ends up being things like faults or shear zones. So that's why a lot of different metallic ore deposits can be focused in those environments, because that's a conduit for fluid to move because it has space to flow in there. And then you have many systems where you have veins. Some examples of the veins here, where the fluid pressure is actually creating its own pathways. So again, many ore deposits form in vein complexes. So that's largely to do with where the fluid is moving and where it's concentrating. So the transport of the metals. Metals are, they're moving as soluble ions, so they're dissolved into the fluid. And they're predominantly moving as cations, so positively charged elements. So they need to bind, or they like to bind to something else to sort of move through. And these are called ligands, the technical term, but they're usually anions. So they're negatively charged, so we have a ability to complex together to balance those charge relationships. And this makes them stable in solution. So that's what they're looking for. So these ligands, depending what they are, we'll go through them in a sec, they're the important concentrations to enable lots of metal to move around. And of course, different metals behave differently, and so that presents complexities, and that's largely based on their charge properties, their valency states, the standard sort of elemental controls that we have when we think about minerals or magmas. We have the same thing going on with metals and fluid and magmas for that matter. But we know that certain metals associate or behave in a similar manner to each other, and this is why you commonly will have mineral deposits with certain groups of elements. So copper, lead, zinc, silver. So lead, zinc, silver, in Broken Hill, Mount Isa, those commonly get those base metals together. Gold, silver, arsenic, bismuth. Again, gold and silver, very common metal association in ore deposits. It's because they behave in similar manners. Tin, tungsten, bismuth, moly, copper, moly, gold. And so have various variations on the theme that relates partly to how they're transported, but it's important to know that different metals behave in similar manners, and that can be a very important vector to help guide you, or pathfinder elements to guide you to an ore deposit. So, the transportation of the metals, the efficiency of the fluid to transport different metals is controlled by its salinity, the type of ligands in solution, its temperature, pH, oxidation state, or redox. So they're the main variables. We've briefly touched on why temperature can be important. Some elements are soluble only at high temperature, and once the liquid cools, they might fall out of the solution. It can also be linked in various ways to how reactions are changing pH or oxidation state, because those ligands will change their form, and therefore how the metals bond with them will vary, and therefore you can get you can either change the solubility or you can deposit the material out. So it's a double-edged sword in terms of how it operates. It can get quite complex, but the main thing at this stage is to realise why these things matter. So salinity, all fairly comfortable what salinity is. So again, depending on the source, So certain elements require significantly saline fluids because they complex with things like chloride, bromine, etc. So copper, lead, zinc are common ones. Other metals matters less so. So gold, silver, arsenic, tungsten, and many others. And so when we get into it with different sources of hydrothermal fluids, this is in part why some systems are mainly associated with certain metals and others associated with other metals. So it all comes back together. So things like metamorphic fluids, meteoric fluids are fairly non-saline. So meteoric one makes sense. Rainwater, groundwater is usually things we can drink, so we're fairly happy. Metamorphic fluids, you know, it's predominantly from a hydroxyl component in a hydrous mineral, so it's pretty pure. There's limited salts dissolved in those minerals unless you have unusual cases like evaporites and things like this. Whereas saline fluids, magmatic fluids, can be much more saline because they have things like chloride and things like that in that. Basin fluids, pore fluids from sediments, makes a bit more sense. You have different cements and things like that, and seawater, surprise. So from a broad first order, you can see how things like orogenic gold likes low saline fluids, so it's more likely to come from metamorphic systems compared to other metal associations. So temperature, probably one of the most important ones. Get into that later, but you know, one, temperature is a catalyst, so things move faster at higher temperature, and solubilities change with different metals. So most are over 100 degrees. Most hydrothermal fluids are generally between 100 and 500 or 550. They're rarely much hotter, but they can be. And in terms of the phase dynamics of fluid, we have what we call the critical point. So we're generally happy with this triple junction, which is solid, liquid, and vapor. So ice, water, and water vapor. But if you move to higher temperatures and higher pressures, we get to a point which we call the critical point. Beyond that, water behaves as what we call a supercritical fluid. And same thing for CO2. I think critical points at different pressures and temperatures. But up here, in essence, its phase relationship is something between a liquid and a vapor. So that's why most of the time in the crust, we discuss fluids, and they're behaving in some manner between these two end members. So the other thing that happens is you can do the same thing with magmas. The critical point is much deeper, at about, I think it's at, I don't know, it must be about 150 kilometers or something in pressure. And the difference between a fluid and a silicate liquid becomes blurred, and they essentially behave in the same way. So that's something important to know. So most of the time, the fluids are supercritical. So pH, this has a big role in the hydrothermal mineralizing system, particularly in what alteration percentages you get. And the pH can change by how the fluid is reacting with surrounding rocks. And so, you know, how these reactions go, you might be contributing hydrogen or losing hydrogen and therefore changing the pH of the liquid. And so this is where it can get complicated with how a hydrothermal moves through the system. It's dynamic, it's changing. So how these changes happen or interact can result in when metals might drop out or when they're more soluble, etc. And so in later on to show the classic case of something like when fluids interact with a carbonate. It's something that's highly reactive and can lead to a lot of metal deposition. So this influences the ligands, all those negatively charged anion complexes that bind to the metals. And so depending on how complexation happens, if it's acidic versus alkaline, will influence which metals and which ligands can complex together to actually carry material. So some, it makes it very difficult to carry metals, others it's more efficient. And yeah, like I said, so the pH is affected by how the fluid might be leaching material from the country rock. And we'll get more into that alteration signature tomorrow. Hydrothermal, so I'll go into this one, but we're fairly comfortable that different magmas are going to have different amounts of water. Subduction zones are more hydrous than mid-ocean ridge. Potentially S-type granites might be more water-rich than I-type granites, but that's a broad generalisation. But the main point is that fluids released from a magma can occur by two main processes, and they might be referred to as first boiling and second boiling. First boiling is related to decompression. So you're releasing that pressure, it's happening quite shallowly in the crust, so the fluid expands, and depending where the critical point is, it might transform into a vapor if you're very shallow in the crust, form fumaroles and things like that. So that's really shallow level process related to decompression. So it can be quite a explosive, maybe not so much, but can have dramatic effects on the country rock, forming breccias and hydrofracturing in the roof zones of granites, which presents a nice void for fluid to move up and around and react and potentially deposit metals. The other case, sometimes called second boiling, this happens deeper in the crust, and this one's primarily related to the fact that this is just a phase diagram for a granite with temperature versus pressure. If you just crystallize at a constant pressure, so you're cooling the magma, water gets fractionated and concentrated into the last little bit of the liquid, and eventually you get to a point where there's too much water, it saturates or egresses out of the, dissolves out of the magma as a fluid phase, as water potentially mixed with CO2. So this process happens deeper in the crust, and it's less sort of disruptive. It's sort of, the water will move out into the local country rock. You might be less likely to form prominent breccias and things like that. So they're the main cases how you resolve magmatic fluids, and they have an influence on the nature of those fluids and potentially their metal concentrations. So which one do you think would be better suited to having a high metal content, taking into account that which magmas usually form shallow in the crust versus which ones form deeper in the crust? As a very broad generalisation.
Yeah, I guess the deeper crust brings up a lot of the newer minerals that haven't sort of reached the surface at all.
Yep.
Potentially that.
Potentially that one, yep. So it can have base ones. The advantage of this one though is you can fractionate the magmas a lot more. So potentially certain metals or lithium and things like that that don't like going into mineral phases get really concentrated up here.
Okay.
So the nature of these fluids, you see, automatically have a bearing on what you might be looking for. Yeah, so this is broad you've seen this figure before, but this would be a case of first boiling up in the top part of the granite, and it essentially cooks there in its juices. This fluid alters the top part of the granite and the country rock and produces certain types of mineral assemblages related to that movement of fluid, its hydration, its cation exchange, etc., changing of pH, and we can form different offshoots of veins, whereas potentially down here you might have more of effect of secondary boiling. Seawater, okay, it's mildly saline, so mostly sodium chloride, but we also have magnesium, potassium, calcium, hydrogen carbonate or bicarbonate. There's essentially no sulfur, fairly low temperature, and we pour concentrator of base metals. Is oxidized and neutral pH. So it's a very different beast to some of the other cases. And we've sort of gone through some of this. I won't dwell on it too much, but it is modified as it flows through these fractious settings. It goes from oxidized to reduced. So we reduce sulfate to sulfides. So automatically we have different metal associations in the metal sulfides. It's better for carrying metals. It's dissolving silicates, and so we've sort of discussed this, how it circulates through, so I won't dwell on that process of how it's recharging and taking on base metals. And the fluid becomes, we might unstable things, form different minerals. Magnesium is lost into the country rock, so we go through an alteration type called propylitic alteration, where we're increasing the magnesium content. It could be moving calcium around, the fluids are changing their pH, and then they're getting hotter. So then they cycle back up, and then depending on the nature of these fluids, you get these different metal associations that we discussed the other day. So copper, potentially gold, probably in the recharge zones, and then out of the black smoke is where we interact this hot fluid with cold seawater of a different oxidation state, of a different salinity, and a different temperature. You can enable the solubility of those metals changes, and they are lost to the system. So you can see how it's a complex and dynamic process, and so it's not as simple as all fluids are the same or similar. They're changing, and that changing dynamic is important for where metals will be found. Meteoric water, oxidized because it's coming through the surface. This includes groundwater, and it'll slowly change its properties, but generally it's fairly low, it's not very saline, and it's got a neutral pH. In contrast, conate waters, again, neutral, but they might be more saline because they're sitting around with other cements. And their oxidation state could be slightly variable depending how deep and shallow they are. So metamorphic water, got through this, expelled through dehydration of hydrous minerals to anhydrous or water poor minerals. You get carbon dioxide. So they're commonly fairly rich in CO2, related to breaking down of things like calcite, dolomite. They're sulfur poor, low salinity, there's not many salts down there, and they're generally reduced. The main source of metamorphic fluids is sedimentary rocks, and they're commonly a graphite bearing. So that helps to influence its redox state, so it keeps them fairly reduced. Okay, so like I said, most of these systems are more complicated than they seem. You guys will be aware of this picture. Hopefully it's not causing nightmares. But you generally will have multiple stages of fluid introduction or the changing properties of the fluid, and that's actually something we need. But we can use evidence, our standard sort of geological laws about cross-cutting relationships and timing of different features to get an idea of the history of that system. So, here's a common scenario. Exsolution of a magmatic fluid leads to alteration of high temperature minerals. This scenario might not be applicable to this case, by the way. Well, I don't think it is applicable. As time progresses, the temperature cools, the composition of the magnet field changes. Cooler temperatures minerals form, things like arsenic pyrite, so iron, arsenic, sulfur. Then later, lower temperature meteoric fluid might circle through and interact with those hydrothermal minerals, precipitate over pretty assemblages. Or it could happen at the same time, where the magmatic and the meteoric fluid interact. It could be like epithermal gold systems, where we're in that sub-volcanic environment, where you have magma chamber material and you have meteoric fluid flowing through, and they could interact. And that could be an area of importance. So how do we know this? Most important question. Am I just completely bullshitting everyone? Probably, but we can back it up a little bit. So the first thing we can do is we can look at things like alteration, salvages, and products. So how do we get those minerals? We can do experiments. We can also go to the source and look at fluid inclusions. These little guys in minerals, you might have seen them before, but they're very small and they have little bubbles in them. And they normally form these sort of, call these negative crystal shapes. So it's almost the opposite of a euhedral crystal, if you like. We have these curved deep boundaries. And they're little bits of fluid trapped in the mineral. And we can analyze them, and we can determine things like temperature. So when the fluid inclusion actually, see how it's got a little bubble here? What happens is the saline brine separates from usually the water-rich component, because they get to a temperature and they're immiscible. So it's like oil and water. But if you heat it up, they'll get to a point where they mix. And that temperature actually tells you the temperature of when it was formed. So we can actually determine that quite simply by looking at physical properties. We can measure the salinity. And then we can start to think more about how was the metal deposited? Is it related to its boiling? Was it related to mixing? Do we see a variety of fluid inclusions? Et cetera, et cetera. So there is ways to piece this together outside of we're just making it all up, which we generally are. And like I said, hydrothermal minerals. So what's in the vein is very important. What minerals are there tells us what the environment was like, what minerals are outside it. And so we use a variety of tools at our disposal. Like most aspects of geology, we use petrography, we use lab work, we use geochemistry, and things like that. So like I said, pH, temperature are very important in many common hydrothermal minerals, and the species that they form at, so what specific composition they have. And this is where we're starting getting into looking at hydrothermal alteration. So what are the products in the surrounding rocks that help us and provide vectors to looking for ore deposits? Hydrothermal alteration is reasonably common, but it's not necessarily pervasive. So these different things can help us guide us to these cases where it is important. So here's a complicated diagram that doesn't really matter until we get to the intensive school, however that works. But when we start to look at alteration products and to think about what conditions they formed at. So it makes a bit more sense when we show some examples, but we have temperature changing on the y-axis, pH changing on the x-axis. The different colours represent different styles of alteration, which we've given fancy names to things that are generally, you know, they're not as complicated as it seems. They're usually dominated by a couple of minerals. So potassic alteration, surprise, surprise, is dominated by potassic minerals. Okay, feldspar, could be muscovite, biotite, these things down here. But there should be some wider ones, sorry. Anyway, you know, and idyllic is largely related to clays and things like that. So when the clay minerals are stable, and then propylitic is largely related to when you have chlorite, things like that. So at the moment, it's just to be aware that we'll get different mineral assemblages depending on, one, the host rock, two, the pressure temperature conditions, and three, the composition and behaviour of the hydrothermal fluid. And we'll go through this a bit more tomorrow about which ones to expect and what they're suggesting. But they can all be put together to you know, reassess how that system formed and what its behaviour is like, and does that mean we're getting close to a certain metal association or not? So we'll get into that a bit more later on. An oxidation state is another important thing. So as a broader case, iron 3+ is less soluble in water than iron 2+. And uranium 6+ is more soluble than uranium 4+. So depending on how oxidized or reduced that system is, certain elements are more or less soluble. The other important state is it commonly controls the form and nature of the ligand. So, you know, is it sulfur dioxide or hydrogen sulfur, and etc. And that actually controls how much metal can be transported. Okay, so getting into some of the nuts and bolts. This is when anyone that doesn't like chemistry starts to hate life. But we don't have to go into it in great deal. But essentially, how metals complex with ligands, which ligands they complex with, is can be broadly systematic. And it's related to, we can classify minerals as hard acids. So most of the metals, so we're looking at the cations here, can be hard or potentially soft. So classic hard ones, where are we? And tungsten, platinum group elements, moly, tin, and things like that. Soft, gold, silver, copper, and we have things that are in between, zinc, lead, etc. And different valence states. So copper 2+ versus that's just copper plus. So hard acids bind with hard bases. So these are the ligands, the negatively charged anions. So these guys bind better with these ones. So opposites attract, they balance themselves out. Soft ones, vice versa, they bind mostly with soft bases. So over here you have things like fluorine, water, hydroxyl, you know, carbonate, potassium phosphate, whereas over here we have bromine, just carbon monoxide, sulfur, hydrogen sulfur. So we have these different associations. So gold is commonly carried in the hydrogen sulfide, and this is in part why processing of gold involves cyanide, things like this, because that actually helps to break down those bonds. So that's the broad principle, and borderline, you know, there's somewhere in between. And in detail, the hard acids prefer an ionic bond, whereas soft acids prefer covalent. So the chemistry is slightly different. And these ones, the borderline chloride is a borderline ligand, so it can actually bond with a variety of ones. So that's why it's a commonly sought after indicator for hydrothermal fluid compositions. So this is a bit more detailed and looking at specific metals, if they're hard acid, hard base, or borderline, and the ligands that they commonly complex with. So, yeah, and remembering there's different valency states of the metal, and you can see if the oxidation or reduction scenario changes, we may have the change in how the ligand, how it bonds with different ligands, or it might lead to metal dropping out of the solution because it no longer has a way to complex with something else in the fluid. So it's essentially turned into a loner, kicked out of the building and said, get out of here. So that can be related to oxidation, could be related to pH, you know, your hydrogen sulfur, if they change and there's no chlorine to bind with, gold or silver may not are no longer stable in the solution and they drop out. Or vice versa. We may need that change in pH to actually dissolve the material into the veins. So there's a variety of complicated mixes. It's okay that you don't memorize them all. It's just to start to realize that it's a dynamic system, and so we're interested in both ends of the spectrum. So one, we need a fluid which has the right ligands to transport certain metals. So that's good to start with, but we also need a scenario where there's a change in that system so the metals are lost from the hydrothermal fluid. So concentrated, then lost. So as you move through and you alter, as a fluid's moving through a rock and is altering, potentially it's changing its pH, its salinity, its redox state, that can lead to changes in that dynamic, which might deposit some metals and dissolve others, or vice versa, or both. So that's the crux of it. That's it for today. Was there any questions on that?
I just had a general, just like,
Yep.
word question. Yeah, it's like here it sort of says like hard acid and soft acid.
Yeah.
When I did chem, it was all sort of like strong acid and weak acids.
Yep.
What's the sort of difference there?
I think it's just geologists being weird.
Alright, I figured.
We like to do that. Yeah, and you know, the classic one is, you might have seen too that geologists used to refer to felsic rocks as acid.
Yes, I've seen that.
And
Yeah.
mafic rocks is basic.
Yep.
And this harks back to this. But you know, in reality, there's no difference in pH. Well, the they're broadly, there's no classic difference in pH for those
Yeah.
systems. It's just something that people go, oh, they've got all the alkalis versus these ones, so we're going to call them bases and acids. So yeah, geologists are.
Yeah, I think that makes a little bit more sense because I remember learning and being like, but like why the acid? Yeah, why is that being called an acid when it's not like presenting? Yeah.
No, exactly. Yeah.
Yeah.
So we have these proliferation of terms that aren't appropriate, or we use them inappropriately,
Yeah.
and we create our own, as you've seen, just to make life difficult. Yeah.
Yeah, that's right.
Got any key ones in there that are worth memorizing?
The gold ones are pretty important.
Yep.
Hydrogen sulfur, chlorine, chloride. That's a pretty good one to memorize because you get a difference in this pH. Yeah, we'll get more into some of the other ones later when we look at acid mine leaching and things like this. So like the sulfide ones become pretty important because a lot of metals are associated with sulfides. And then you also get the effect of, we bring all this ore material up onto the surface, expose it to rainwater and things like that, and drainage, and it reacts again, of course, by this oxidation, and we create acidic water that, out of these tailing dams that goes off into the environment. So, it's our friend and it's our worst enemy. So yeah, the sulfide ones usually become fairly important. But yeah, gold's a nice one to think about in a simple sense. Some of the base metals get a bit complicated. Tungsten works okay as well.
Okay.
But yeah, Rob does a fairly good job. Yeah, it gets a bit complicated. And I wouldn't expect you to be, not going to just go, oh, here's some weird transition metal that I expect you to learn to know how we'll go with samarium or something.
Would it still be acceptable to just sort of say like strong and weak?
Yeah, that's fine.
Yeah.
I'm not going to get fun with that.
Yeah.
I'll be like, no. For me, personally, especially at your stage, I'm less worried about terminology. My opinion is if you can describe the feature and you can't quite get the term, that's okay. You'll get the term eventually, because once you get to a point, it becomes easier with those. But we have a habit of hiding behind them. A lot of them are just broadly like, oh yeah, okay, some specific term. Say, take a phenocryst, for example. That's one. If you say there's a coarse crystal in a matrix of fine crystals, well, yeah, okay, that describes phenocryst. Excellent. You're getting the point. If you know it's a phenocryst, great. But knowing it's a phenocryst versus the description, there's no greater, it's just like, okay, great, someone memorised the terms and someone did. You described the rock adequately as it is. So at this stage, worry about describing the process and getting there. If you use the terminology, is great. If you can't remember the terminology, work through it. Don't worry about it. It's about learning the principles. The process is most important, and the terminology will come. Because geologists are terrible with terminology. Many geologists are terrible with pigeonholing. And a lot of it stems from, in the past, is they didn't know what was going on. So, we'll pigeonhole everything. Economic geology is classic for it. It's really frustrated me as a student. Is you go, fundamentally, what is the process that's controlling it? That's the part that groups them all together. Then you have subtle variability. So that's another piece of advice for this. You'll go through the textbook. We're going on about, this is a Cypress type BMS deposit, and this is the Valley type or whatever. And it's like, yeah, okay, there's a few examples that are meaningful, but it's worrying about the process, because that's what's going to help you find another one. It's not going, is this Cypress type or You know, it's like, this is it. This is the kind of environment I'm in. What should I expect? Oh, that doesn't fit with this, so maybe there's something else going on. And work more that way. So think about the broader classifications is what I think are most important. Is it hydrothermal? Is it sufficient? And why is that the case, and what do we expect to see? And less so about, some of them are great. It's only got a broken hill type because it's experienced metamorphism at 800 degrees. Most ore deposits don't even get anywhere near that. So it's like, why does it have to be a tight thing? And so a lot of that was built around, people didn't know, so they grouped. So yeah, don't get too caught up with that. Process is king. If you understand the process, you'll be able to find another one. If you get caught up being like, I'm looking for Broken Hill, you'll probably never find it. So anything else, or we're good?